Okay, today what we're going to do is we're going to talk about naming and start looking at some of the preliminary reactions of the carboxylic acid derivatives. So first thing is that the definition of a carboxylic acid derivative is one that gives a carboxylic acid when it's hydrolyzed. And a hydrolysis reaction is when you react with either H plus H2O or hydroxide and H2O. Those conditions are called hydrolysis. So every single one of these carboxylic acid derivatives, the acid chloride, the acid anhydride, an ester, and an amide, give carboxylic acids when they are hydrolyzed. And we'll talk about the mechanism of each one of these. Some of the mechanisms are pretty straightforward. Other ones have semi-magical steps to get them to the final product. So this is over the last couple lectures I've talked about having carboxylic acid derivatives with the Y group, and in this case I've shown you the Y group. Now I've put the carboxylic acid group in here just in terms of its relative position. So looking at these again, the most reactive is an acid chloride. The least reactive is an amide. And part of the reason that we explain that is because if you have a chloride, that's the best leaving group, then this carboxylate would be the next best leaving group, hydroxide next, OR a little more difficult to leave, and then N would be the most difficult to leave, although for esters and amides, I'll talk a little bit more about why they are the least reactive. So we're going to go through and name some of the, we're going to name a few of these carboxylic acid derivatives to start with, and I'm not going to go through an extensive naming list here. I'm just going to talk a little bit about the basics of naming these. So first of all, if we start with an acid chloride, we know that the acid chloride in this case has a halogen attached to the carbonyl group. And the way that we name this acid chloride is to name the carboxylic acid that it came from. And so if we had, for instance, something simple like this, the common name of the carboxylic acid that this acid chloride came from is acetic acid. And its IUPAC name is ethanoic acid. And so the ANOIC acid is the suffix for the IUPAC system for naming carboxylic acids. So when you convert a carboxylic acid to the acid chloride, what you do is take the name and you're basically going to add a YL to this, and the YL is going to be is going to replace the IC in both of these cases. So this would be called acetyl chloride, would be its kind of common name, and ethanoyl chloride would be its name for the IUPAC. So we can actually name these either common names or the IUPAC names. So that's the basics for naming those. So name the carboxylic acid and then just remove the IC ending, add a YL, and then add a chloride. If this is a bromide, it would be acetyl bromide or ethanoyl bromide. So naming acid chlorides is relatively straightforward. Now, naming esters and lactones, and we've talked a little bit about lactones, and I'll come back to, I'll remind you of that here in a few minutes. But if we're looking at the esters, we have to understand exactly what we're looking at when we look at a carboxylic acid ester. So if you look at, let's say, something simple like ethyl acetate, and I'll come to that name in a minute, esters, we know one of the simplest ways of making an ester is to react a carboxylic acid with an alcohol, Fischer esterification. So when you look at an ester, you have a carboxylic acid part, and that is here, and then you have the alcohol part from there. So here's your carboxylic acid portion of the ester, and here is your alcohol portion. Now when we write the name of an ester, what we do is we simply take the alcohol portion and we write what alkyl group that alcohol portion has. So for instance, we would call this ethyl for the fact that it comes from ethyl alcohol. Then we would name the acid. So this is ethyl the acete, and now instead of this being acetic acid, this becomes ethyl acetate in the common name. So in the common name system, I'm going to change the acid part from acetic acid to acetate. In the IUPAC system, we still would write this as ethyl, but now we would write this as ethanoate. So I'm replacing the IC with an ATE suffix in both cases. And this would work for any of the acids. So for instance, if I had something like, there's something a little more complicated here. Let's say that I had, let's say I had this. The first question would be, okay, here is my carboxylic acid part. What do I call this? And this would be a cyclopentane. I'm writing this in the IUPAC system now. This would be cyclopentane, and then it would be carboxylic acid normally. So this is going to become cyclopentane carboxylate would be its name. Now as far as this part coming from the alcohol, we could write this as potentially isopropyl, or in the IUPAC system, again, this would be a 1-methyl F group. So in the IUPAC system, I would call this 1-methyl ethyl, and that would probably be best to go in brackets. And then it would be cyclopentane carboxylate. Okay. Or the other thing you could write is isopropyl cyclohexane cyclopentane carboxylate. Right. So we always name the alcohol part and then the acid part, so using the same rules as we would use for acids, except we would add the ATE suffix instead of the ic for that. Instead of the carboxylic acid, it'd be a carboxylate. As far as lactones go, we've talked about lactones. A lactone is a cyclic ester. How did we make lactones? If you remember, we made lactones by taking ketones and doing the Baeyer-Villiger oxidation on them to insert the oxygen. As far as naming these goes, we actually use for the lactone, we write the term lactone at the end, and that indicates that it's a cyclic molecule. Now in this case, the way I would write this is I would say that this came from a 1, 2, 3, 4, 5. So the way we would name this in this particular case is this would be called 5-hydroxy, because that's what it came from. And then we have a 1, 2, 3, 4, 5. This is a 5-carbon acid, so this would be a pent and oic acid lactone would actually be its name. So the 5-hydroxy tells us that's where the O that's attached to the carbonyl is of the ester. So it's a 5-hydroxy pentanoic acid lactone would be its name. And so we don't normally name those a lot, but that's how we would do it if we were to name those. Naming anhydrides. Well, what is a carboxylic acid anhydride? Carboxylic acid anhydride has, in essence, 2 carboxylic acids linked together by an oxygen. And so that would be the anhydride. Now, how do we name anhydrides? Well, in terms of naming carboxylic acid anhydrides, what we would do is name, in essence, both acids that are attached to the oxygen, followed by the word anhydride. So if I had, for instance, one of the simplest anhydrides that people use a lot is this one, which basically this is the anhydride of acetic acid. We would actually just call this acetic anhydride, and it's understood that both of the carboxylic acids that made the anhydride are both acetic acids. Now I should probably take a step back here and say that when you're looking at an anhydride, the way we can think of forming this is to take 2 carboxylic acids and bring those together in loose water. So that's where the term anhydride comes from, is the fact that we've lost water between 2 carboxylic acids to make the anhydride, the molecule without water, or the anhydride. So if we have an anhydride here that has the same carboxylic acid on both sides, then we just use that one name. Now if I had two different carboxylic acids, so let's say something like maybe this one. Now looking at this came from acetic acid and formic acid. We could call this one acetic formic anhydride. And so that would be very descriptive, and that would actually be what we would call our common name. Now as far as the IUPAC name goes, there's really not that much difference. Instead, we name the two acids according to the IUPAC rules. So in the IUPAC system, this would be acetic, or no, it wouldn't be acetic, it would be ethanoic, because that's the 2-carbon acid, and then methanoic anhydride. So that would be its IUPAC name. And if you had substituents off the carboxylic acid group, then you would include those only, just call it OIC, and then add the anhydride afterwards. Amides and lactams. So an amide has a nitrogen group attached to the carbonyl. We can again think of those as coming from a carboxylic acid and an amine. So in terms of naming the amides, we want to think of that sort of breaking apart as being the way to name this. Now, the only thing here is that what I'm going to do is I'm going to name the acid part followed by the amide sort of suffix. So for instance, let's take something fairly simple. Let's take acetic acid and then put NH2 in front of it. So this would be called acid acetamide would be its name. So it's the amide of acetic acid. Let's take another one here. Now let's add 2 methyl groups to the carboxylic, or to what would be formic acid. Now in this case, I have 2 methyl groups and I have to distinguish that the methyl groups are attached to the nitrogen and not the acid part. So how do I tell that groups are attached to the nitrogen? I put an N in front of it. And so this would be NN dimethyl, and now this would be called formamide. That would be its IUPAC name. If I was to do this, if I was to look at this molecule in the IUPAC system, I again would actually call this NN dimethyl methanamide. So for the we actually use the methan, ethan, propan term. So we're in essence dropping the OIC and adding AMIDE. So this would be NN dimethyl formamide, or NN dimethyl methanamide would be its name. So these are the different ways, and an amide is slightly different in terms of, well, it's not that different. Instead of this being acetic acid, it becomes acetamide, or becomes acetamide. And if this was the IUPAC name, this would be called ethanamide, would be its name. So if there's alkyl groups attached to nitrogen, just put your N's and the correct number of N's. If there's 2 alkyl groups, you need 2 N's. If there's just 1, you would put 1 in front of it. And actually, you would put a 1 in front of each one. Let me do one more example here. Let's take this one. Let's attach a methyl group here and an ethyl group here. So writing this one, this came from, let's write the IUPAC, this came from butanoic acid, and there's a methyl and an ethyl. So what we would actually do is we would say this is N-ethyl, and then specifically say it's then N-methyl, so there's no confusion that the ethyl and the methyl group are both attached to nitrogen, and then this would be butanamide. So it'd be N-ethyl, N-methyl, butanamide would be its name. Okay. Lactam is nothing more than a cyclic amide. So if we're looking at a lactam, let's say I've got the 5-membered ring here. What I would call this, and this gets to be a little bit strange in the way that they do this, I'm going to do the same thing as I did before, only I've got a carbon 1, carbon 2, carbon 3, carbon 4. So remember how in the case of the lactone, we called this a 5-hydroxy. We call this a 5-hydroxy pentanoic acid lactone. I'm going to do the same thing here. I'm going to call this now a 4-amino, and this is now going to be 4 carbons, so this is going to be butanoic, and now I'm just going to say lactam. So when I'm reading this name, I know that my nitrogen that is attached to the carbonyl is at carbon 4. It's a 4-carbon chain, and so it comes from butanoic acid, but this is the lactam. So I'd have 4-amino butanoic lactam. So that would be its name. Now another functional group that does hydrolyze to give carboxylic acids but doesn't fit that overall general rule of having the carbonyl attached to this Y group are C triple bond N groups called nitriles. We're going to find, well, we actually already have found that if you take a nitrile and react it with acid and water, that you form a carboxylic acid. And you may say, well, when did we do that reaction? Well, if you remember, we took a ketone or aldehyde and we reacted it with HCN to give us our cyanohydrin. I'm going to just erase this whole thing. And we'll make this an aldehyde just to be on the safe side. So what I ended up doing was I ended up forming my cyanohydrin. And then what happened next? Next I reacted it with H plus H2O, and that hydrolyzed the nitrile group to form what we called at the time an alpha-hydroxy carboxylic acid. So we've already seen the hydrolysis of a C triple bond N will give us a carboxylic acid. Therefore, it is classified as a carboxylic acid derivative. So how do we name nitriles? Well, the nitrile is going to come at the end of the name. So let's take something fairly simple and write its IUPAC name. Here's a molecule. This has 2 carbons in it. So this would be called ethane, except actually they put the E in, so this is called ethane nitrile would be its name. Now, nitriles automatically, if there's no other higher priority functional group in it, are going to get carbon 1. So I'm going to say, okay, this is carbon 1, 2, 3, 4, and 5. So this is going to be a pentane nitrile, and you don't need the 1 because it's assumed that the nitrile is automatically carbon number 1. And in this case, I would say this is 3-bromo pentane nitrile. Okay. Now, if you were going to name this molecule up here according to its common name, what you would do is you would take this part and you would say, okay, that 2-carbon, since this is a carboxylic acid derivative, that would be acetic for acetic acid. And in this case, we would call this, we add an O in, so this is called acetonitrile. So this part comes from the number of carbons that basically treating nitrile as if it was a true carboxylic acid derivative in this triple bond N was a Y group. So down here we'd have to remember what the 1, 2, 3, 4, 5 carbon acid is, and that's valeric acid. So you could actually call this either 3-bromo valerionitrile, because the 5 carbon is valeric acid, or sometimes people will use the Greek lettering for this. And the problem is the Greek lettering system would actually start at the carbon next to the carbonyl. So this would actually be called beta-bromo valerionitrile. So we won't worry about the Greek lettering system for the moment. But basically in your IUPAC naming, you just take the number of carbons and then write whether it's an ethane, methane, propane, butane, etc. But the nitrile is automatically assumed to be carbon number 1. So what happens when you have multifunctional groups? Well, earlier in the semester I kind of screwed up when I said that the naming priorities matched with the Kohn-Ingold pre-log sequence rules. If it would have been me and the IUPAC committee would have asked me, that's what I would have made it as. But they didn't ask me, and so they didn't do it that way. So here's actually a list, and this is table, if you're looking in your book, this is table 21.1 from your textbook, where the functional group, the name of the group when it is the highest priority in the molecule, or the name of it when it's a substituent, is listed, and it goes from the highest priority down to the lowest priority group. So it turns out that carboxylic acids are the highest priority, then esters, then amides, then nitriles, then aldehydes, ketones, alcohols, amines, alkenes, alkynes, and alkanes. And you never have an ether or a halide as basically being the parent name for a molecule. And if you go back and remember what we did with ethers, we always had the ether parent name be an alkane with an alkoxy group attached to the alkane. So you look at this list and find the highest priority name, and then everything else becomes a substituent. Now, you could say, but if carboxylic acid's at the highest, if it's the highest priority, then when would it be called a carboxyl? Well, that would happen, just as an example, what would the name of this carboxylic acid be? Well, if you remember, this is called cyclohexane carboxylic acid. So typically when these groups are attached to aromatic ring, or not to aromatic rings, because aromatic rings are a whole different ballgame, but when they're attached to a cycloalkane ring, then we use the term carboxylic acid. Going back to this, remember that we had for our aldehydes, we had those being, what were they called? The aldehydes were carbaldehydes. Now actually the name as a substituent is kind of a common name system. Like the hydroxyl group, remember we could call a hydroxyl a hydroxyl. So some of these we actually will use when a carbonyl group, when a ketone is in its, when it's a substituent, it's called an oxo group. When an amine is a substituent, it's called an amino group. When an amide is a substituent, it's called an amido group. Or we have, for the esters, we would have an alkoxy carbonyl group. Some of these will deal with, some of them they won't. But here's some examples. this is the molecule that we actually used in lab last semester when we did our yeast reduction. This molecule was called ethacetoacetate. Now, that's its common name, and basically the aceto part, I'll write this name up here, the ethyl part came from the ethyl alcohol part of the ester, and then the aceto part came from this group basically being the keto group. So, and then this group right here came from the acetic acid, only it's the ester of acetic acid, so ethacetoacetate. There. But its IUPAC name, we would look at these and we would say, okay, I've got a ketone functional group and I've got an ester functional group. I got to go back to my chart. And so the ester comes first. So this is going to be an OATE suffix. So I would come over here and I would say, well, this is a 1, 2, 3, 4. This is a butanoate. Right? This is an ester that came from butanoic acid. What would come first? Still ethyl. So this is going to be ethyl something butanoate. Now, the keto is at carbon 3, and if I come back here, I would see that it actually says that ketone group is called an oxo group. So what this would actually be called is, it would be ethyl 3-oxo butanoate. And so it's the ethyl ester of butyric acid, and it has an oxo group, meaning a keto group at carbon 3. So its actual IUPAC name would be ethyl 3-oxo butanoate. Now, this molecule right here is abbreviated 4-HNE for 4-hydroxy-nonenal. It's a compound that one of the research students that's working with me, we would hope to find in an oxidation reaction we're looking at by GC mass spec. We haven't found it, but it's there somewhere. Now, if I'm looking at this, I see I've got an aldehyde functional group, I've got a double bond, and I've got an alcohol. So we go to my list, and what does my list say? My list says the aldehyde comes before alcohol, comes before alkenes. So the parent name of this is going to be a something ANAL. That's going to be its name. Now, since this comes at the end, I'd automatically number with the aldehyde being carbon 1. So if I look at this, this is actually a 9-carbon aldehyde. So this would be called non, and then the al. So there's probably a couple of ways to handle the double bond versus the hydroxy. So what we would do with this is actually the double bond, we would say this is we could do this one of two ways. We could call this 2-non-enal, or we could probably call this 2-enal. I like 2-non-enal, but you kind of get the gist of this. And then there would be a hydroxy group here, so this would go 4-hydroxy 2-non-enal. We've almost got the name, except that this double bond has a E stereochemistry. I suppose you could say trans. So either you would say this is E 4-hydroxy 2-non-enal, or you could also call it 4-hydroxy 2-E-non-enal. So I'm just kind of giving you a little bit of a taste for the rules here, because they really do get complicated when you have a lot of multifunctional groups. This molecule right here is, I believe, called geranol. It's an ester that you find probably in geraniums, hence the name. It's a molecule that's found in a lot of fragrances. So looking at this is going to be a little bit different because here is my carboxylic acid part. So in the IUPAC system, this would be, well, it would be an ethanoate. In the common name, it would be acetate. The real question would be then, what would this alcohol be called? So we've got 1, 2, 3, 4, 5, 6, 7. So this is a, let's see, 2, 3, 4, 5, 6, 7, sorry, 8. It's an 8-carbon alcohol. So there's double bonds between carbons 2 and 6. There are methyl groups at 3 and 7. And there's there's actually one stereochemistry on the double bond that is between carbons 2 and 3. So between carbons 2 and 3, we actually, if I'm looking at this, we have a high priority group there, a high priority group there. So the stereochemistry around this is the E stereochemistry as well. So the name of this alcohol then comes before either acetate or ethanoate. So looking at this, there's a couple of ways that we could do it. I think everybody would agree that this is a 3,7-dimethyl, and then it is definitely an oct or an octa because it's an 8-carbon ring. Then I think we would have the numbers, which would say the double bonds come between carbons 2 and 6, which means this is a diene. And then if that was the alcohol, we would have this being an octa 2,6-diene / 1-ol. But now I'm changing this to the alkyl group that is in front of the ester, so this would actually be 3,7-dimethyl octa 2,6-dienol. That's the alkyl group that's attached to the alcohol part, just like up here. This alkyl group attached to the oxygen is an ethyl, so this would be, actually I'm forgetting E. E3,7-dimethyl octa 2,6-dienol. That's the alcohol part, acetate or ethanoate. So what's my point? My point is that naming multifunctional groups can be quite difficult, and getting exactly the correct syntax and exactly the correct name can be challenging. And I actually have a number of computer programs that I can type in the structures and it'll give me the names, and not all of those programs agree with one another. If you really wanted to get into this, what we would use is what's called the IUPAC, what's called the Blue Book, that has all of the rules for naming everything. But it's kind of like writing a law if you're not a lawyer, or reading a law if you're not a lawyer. Unless you're like really up on your IUPAC Blue Book rules, it becomes a little difficult. So I'm just giving you kind of a taste of naming these. All right, let's get back to something a little bit more important here. Not that naming's not important, but it gets frustrating after a while. Let's look at basicities of the nitrogen and oxygen and amides and esters. So if you have an ester, or if you have an amide, we know that the oxygen of the carbonyl, both this oxygen and this oxygen, those are both basic. So if you were to add a proton, you could easily protonate the carbonyl oxygen. Can you protonate the ester oxygen that comes from the alcohol? Can you protonate the nitrogen that comes from the amine? Well, no. And here's why these are not basic. So looking at these two, those two atoms are not basic in both cases. And you may say, well, why is that the case? Well, there's actually another resonance structure that I can draw for my ester. Let's say I take this pair of electrons and I move it here, and then give that pair of electrons to the oxygen. Well, the other resonance structure that I can draw for the oxygen would look like this. The other resonance structure, if I did the same thing for the nitrogen, move this pair of electrons here, move that pair of electrons there, the other resonance structure that I could draw for that would be this. I'll just go ahead and put two R groups there. Now, you might say, yeah, so what? Well, the so what part of that is if I was to write the resonance hybrid for these two, the resonance hybrid would look like this. We would have, in this case, in essence, a partial double bond with the oxygen having a delta minus charge, and I would have a partial double bond to this oxygen with the oxygen having a delta plus charge. If I came down here and wrote the resonance hybrid of this, it would show a delta minus on this oxygen with a partial double bond, and then a partial double bond to the nitrogen with a delta positive charge on that nitrogen. So when you look at these two resonance hybrids, what you immediately see is you see the delta plus charge is what's going to keep that atom from accepting the H+. And so the reason that the nitrogen and the oxygen of an ester or an amide is not basic is because you can form these resonance structures, and therefore you can have a delta positive charge on those two atoms. Now I'm going to come back to this in a few minutes. Because of these resonance structures that you can write here for the ester and the amide, it turns out that these two are actually a little bit more stable than your run-of-the-mill carboxylic acid derivative because of those resonance structures that you can actually draw. And so that's going to make these a little less reactive when we're adding nucleophiles. But the oxygen and nitrogen of esters and amides is not basic for this particular reason. So looking back then at our carboxylic acid derivatives, it turns out that if we do have the acid chloride being the most reactive, and then we have the amide and ester being the least reactive, and again being a little bit more stable because of those resonance structures, when I say that the acid chloride and the amide, they're most and least reactive, well, what am I talking about? And the reaction that I'm talking about is this one. Take this, add a nucleophile to it. Let's just say for the sake of argument it's a negatively charged nucleophile. Have that pair of electrons attack that carbonyl. we know that we form this, right? And then we bring this pair of electrons back down, and we either kick off the Y group or the nucleophile. Let's kick off the Y group, so we lose Y minus, and we end up doing what's sometimes called nucleophilic. It's called nucleophilic acyl substitution. Not everybody calls it this, so it's not as widespread as electrophilic or nucleophilic aromatic substitution, but you can call this nucleophilic acyl substitution. So that's what I'm talking about when I say an acid chloride is much more reactive than an amide. And the only question is, what's the nucleophile? And will the nucleophile leave as opposed to the Y group? But here's what can happen with these carboxylic acid derivatives. I could take an acid chloride and I can make an ester out of it. Or I'm sorry, an anhydride out of it. I can take a carboxylic acid and make an ester out of it. Well, we know that. That was the alternative to Fischer esterification. And we saw in some of the last lectures that I could take an acid chloride and convert it to an amide. So we can convert a molecule above to a molecule below. And we're going to go through the mechanisms of these different transformations as we go through each one of these functional groups from acid chlorides down to amides. So we're talking about nucleophilic acyl substitution as our reaction. Well, we've already seen that the nucleophilic addition to the acid derivatives occurs by this mechanism. So this mechanism was going to go on this slide. And then the amides and the esters are also less reactive due to their resonance stabilization, which is on this slide. So even though I planned these slides out, I'm still freewheeling here, so I've already talked about these two things. So now I'm back to my carboxylic acid derivatives. Well, here's what I want to do. I'm going to take each one of these individually. So I'm going to talk about acid chlorides. Its preparation, its reactions. Then anhydrides, its preparation, its reaction. Now, one of the things that every one of these things can be converted to is a carboxylic acid. So hydrolysis then will take the amide to the carboxylic acid, the ester to the carboxylic acid, the anhydride to the carboxylic acid, and the acid chloride to the carboxylic acid. So every single one of these carboxylic acid derivatives can be converted to a carboxylic acid. And we'll talk about those mechanisms as we go along here over the next couple lectures of what the mechanism of hydrolysis is as well. So, carboxylic acid chloride preparations and conversions. How do we convert a carboxylic acid to a carboxylic acid chloride? I should make this an online quiz question and make you answer it, but hopefully at this point everybody remembers SOCl2 or PCl3 or PCl5. Any one of these would convert a carboxylic acid into a carboxylic acid chloride. Now let's talk about the conversions in terms of the mechanisms. Now, many of the mechanisms I've talked about in previous lectures. But let's take one that I haven't talked about, or two that I haven't talked about. Let's say I react an acid chloride with water. What's going to happen? Well, if you say, okay, I'm going to take this pair of electrons and it's going to attack the carbonyl, I'm going to get this O minus. I'm going to down here have an oxonium ion. and then I'm going to have my Cl minus. Okay? You'd say, but wait, doesn't the acid chloride need acid to have the water react? No. Chloride is pulling electron density out of this carbon. Oxygen's pulling electron density out of that carbon. That carbon is plenty delta plus enough to have a neutral nucleophile like water add to it. And it's not just water, it's alcohol and amine as well. So I formed this compound. Now there's two mechanisms you could follow. You could say, well, let's do an intramolecular hydrogen transfer here, and let's move this proton up here. So you could, if you really want an extra step, you could say, well, I'm going to get this, and I'm going to erase that plus in a minute. So I'm going to end up with this. And then in the final step of this mechanism, I would bring this pair of electrons down here, kick off the chloride, so that I end up losing HCl, and that would then give me my carboxylic acid. So this is hydrolysis, and this is the mechanism of hydrolysis. If you had base, the base would immediately attack the carbonyl. If you had acid, you could make the argument that the acid would protonate the carbonyl, then the water attack. It's all the same mechanism, just different variations of it. So when you take an acid chloride and it comes in contact with water, it forms HCl and it gets hydrolyzed back to the acid chloride. All right, what else can I do with the carboxylic acid? Well, if I work down my chart, and I forget what my chart is, actually I don't, but let's say we went from acid chloride to anhydride. How would that mechanism work? Oh wait, I should probably go back here and say, this is one way to do this mechanism. If you wanted less steps, it would be perfectly acceptable to do the following. Bring this pair of electrons down, kick the chloride off. That would then form this. Now, the oxygen that's attached to the carboxylic acid, this is also not very basic, and so this would immediately lose H+. This would immediately lose H+ to give me my carboxylic acid. So I don't care if you go through this two-step process or this two-step process. It doesn't matter to me because it's basically all the same. Now, if I was a very specific organic chemist, or what I should probably, if I was let's say an analytical organic chemist, or at least the first four letters of analytical, I would actually want to do an experiment to figure out which one of these mechanisms occurred, and that would actually be fairly straightforward, because if I reacted my acid chloride with an oxygen 18 labeled water, and my product ended up with both with a random distribution of O18 in both of these oxygens, then I know it came from this intermediate. If I ended up with only the oxygen 18 in this position right here, then I would know this mechanism occurs. But I'm not that analytical of an organic chemist. I want to make it anhydride. So let's take my acid chloride, and simplest reaction would be to react this with an acetate. Where did this come from? This is a deprotonated acetic acid, or any deprotonated carboxylic acid. This comes in, adds to that carbonyl. Oops. Getting ahead of myself again. Bring this pair of electrons down, kick the chloride off. Voila, anhydride. You could also actually just react the acid chloride with the carboxylic acid, and this oxygen would be somewhat nucleophilic in order to do that reaction, but this would be the best. Okay, could you write the mechanism for taking the acid chloride and reacting it with the alcohol? Could you take and write the mechanism for what am I thinking? Could you do it for that? You know what? I'm bored with online quizzes. And despite the fact that the computer will grade the online quiz, against my better judgment, here's what I'm going to ask you to do. So in lieu of an online quiz, let's make this a take-home quiz. Yeah, let's make it a take-home, non-online quiz. So, your take-home, non-online online quiz will be to write the complete mechanisms for those two reactions. Okay, so that's your take-home non-online online quiz. In other words, what that means is I want you to write out the mechanisms on a piece of paper. I will collect those up. I will grade those as if they are an online quiz, despite the fact that you're doing them on paper, which makes them non-online. So how about we do that? And you say, well, I can't write those mechanisms. Well, this will be a good tune-up before the next exam because you may have to do that from before. So could you follow these steps and some of the other mechanisms that we've done to write those two complete mechanisms? So there won't be an online quiz. This will be your online quiz for this lecture period when this is due, which is Monday. Okay? We want to keep things interesting.